A copper pipe has an inside diameter of 13 millimeters. Water has a density of 1 grams per centimeter cubed and viscosity of 1 times 10 to the minus 3 pascal second at 20 degrees Celsius. I want to take a moment to note that in case that seems a little bit suspicious, why are both of those 1? It turns out at a greater number of sig figs, this one would have been like 0.99 something, but then rounded off, it rounded up to 1. And this one is 1.00, I think 1.6 would come next. But again, at 3 sig figs, it was 1, so that's just maybe a strange coincidence. And the viscosity, both of these actually vary with temperature, but the viscosity I think does a little bit more. But I looked these up for 20 degrees Celsius for writing this question. The question we're asked, though, is at what speeds would the flow of water be laminar versus turbulent in this pipe? So we're being asked for speeds, which means we need to make some assumptions about below which Reynolds number and above which Reynolds number are we going to get laminar and turbulent flow respectively. So we're going to use what's conventional, going to be conventional, or I'll usually use as a convention for this class is 2000 and 4000 for the Reynolds number. To make this easier, I think what I'd like to do is take this expression for the Reynolds number and solve it for speed, or V is for speed here from velocity, right? So if I do some cross multiplying and dividing here to isolate V, I think I'd multiply both sides by the viscosity eta. So I'll put that here in front of the Reynolds number, and then we'd divide by 2 rho r. Okay, and maybe actually what I could do, since I'm given diameter in this question, I think I'll restate this as just rho times Reynolds number n sub r. Sorry, I meant to say eta. That one's eta that I just wrote. Here comes rho, and then I'm going to take that 2 and combine that with the r and just say d for diameter, because then we can just put in that 13 millimeters for that. So, okay, if we want to look at laminar flow, so maybe I'll just write laminar here. And we'll look at what we're going to do for that. So we're going to calculate the speed, and really it's going to be, this is the sort of the cutoff below which we think we're pretty sure it's going to be laminar, but I'm just going to use that formula I just wrote. So it'll be V is equal to, and let's start putting in the numbers we have. So eta's for viscosity, so that's going to be the 1.00 times 10 to the minus 3. And I'm going to track all the units here because I think with fluids, it's good to track units just to be careful and not make mistakes. It's really easy to make mistakes if you don't track units. The Reynolds number we're using for laminar again was 2000, so I'm just going to put that in again. It's a pure number, dimensionless for Reynolds number, so we can just put 2000 and not have to worry about any units for that. Density is given to me as in grams per centimeter cubed, but maybe it'll be easier if I convert that to kilograms per meter cubed, and it turns out that would be, you could check this if you want, 1,000 kilograms per meter cubed. I think the number of significant figures is a little more obscure here in this way, right? But we remember what it was. And then the diameter, that's the 13 millimeters, but maybe I could rewrite that as 0.013, because really that's 1.3 centimeters, but that'll be 0.013 meters therefore, and that might give me some more transparency on units. What do I expect though for units, right? I mean, I converted all of these, it looks like, into base units, right? And we know the pascals is kind of defined based on base units. And since we're calculating speed, it might be reasonable to expect that we would get meters per second. And that's why I did all those conversions the way I did, is like I usually do. When you're in base units, it's kind of easy to predict what units will come out. And if you want, you can always go and check that. Putting these numbers into my calculator, I get like 0.15384615, etc. But maybe we can just round that off to 0.154, since it looks like we're at 3 sig figs meters per second. And then for turbulent, we're going to do some very similar things here. Similar expression. The only difference this time is going to be that instead of a Reynolds number of 2,000, we'll put in 4,000. And again, this, for the laminar, it's that speed or less than that, but for this one, it's going to be whatever I calculate here or greater than that. And in fact, it should be about double, right? Because the only thing that's changing is the 2,000 to the 4,000. And so I'd expect that this result, I mean, maybe there's some rounding could affect it, I suppose. But let's see, if I put that into my calculator, I get 0.30766923, etc. And that would round up at 3 sig figs to 0.308, which I think is exactly double, even after the rounding, of what we had. Okay, so we can go ahead and check that answer now. And things are maybe reported a little bit differently there on the slide. It looks like I chose to go with centimeters per second, but it looks like the actual quantities match. Converting the meters to centimeters, you multiply by 100, right? Something to appreciate with this result, though, I mean, it's an interesting example, right? But can we maybe say something about this? Because I think I'd like to. Does this seem like particularly fast or slow flows that we're talking about with these two numbers here? And I believe the answer is they're relatively low flows. These are relatively slow, that is. In that sense, if I turn on the tap in my house, I mean, maybe it depends on whether the width of the pipe is like this, but it turns out 13 millimeters diameter, inside diameter, is pretty close to one of the standard pipe widths in household plumbing. So this might be representative of that. And what might be more common is like not some fraction of a meter per second, but maybe like at least 2-ish meters per second flow. And it turns out I don't think I have enough space to show it here, but if you go and actually calculate the Reynolds number for this situation, so if I kind of flip the question on its head and I say, instead of like, given Reynolds number, calculate a speed, if I say given speed, calculate Reynolds number, and if I put in 2 meters per second in here and then use the same density and viscosity and the diameter of 13 millimeters, or the radius corresponding to that, the Reynolds number that I get for that is, let me just double check on my calculator. I think it's 52,000, which is huge. And so the takeaway is, if you ask the question, in general, in like household plumbing, is laminar flow common or is turbulent flow common? My answer would be turbulent flow is common. And if you've ever heard water running through pipes and you ask, what is it that you're hearing? Most likely it's the turbulence that you're hearing.